Hi, my name is Victoria de Leon and I'm a Robotics and Digital Systems Engineering student at Tecnológico Monterrey in Mexico. Today, I'll be presenting as part of the RISC program a multimodal wristband for real-time scratch detection in patients with chronic itch, a project from the Robotic Caregiving and Human Interaction Lab in the Robotics Institute at Carnegie Mellon University. I've developed this work under the guidance of Professor Zachary Erickson and the mentoring of Akil Padmanabha, Nathan Sapanelli, and Anthony Burtz. Special thanks to them, and to Carlo Mahidi too for his involvement in the concept of this project. Let's begin with the problem statement. Eczema or atopic dermatitis is a chronic inflammatory skin condition characterized by itching, redness, and rashes. It commonly affects the skin's barrier function, leading to dryness and susceptibility to infections. The condition often starts in childhood and can persist into adulthood, with symptoms varying in severity. As shown in the figure on the right, researchers have coined the term itch scratch cycle to describe the cycle associated with chronic itch. It is just this perpetuating thing of scratching damaging the skin barrier where irritants penetrate, then you have irritation, more itching, more scratching, and it just gets worse and worse. The condition is reasonably well understood, but there is a huge lack of continuous quantitative methods and measures of any steps of the cycle. So we may need to present some facts here. In the United States, about 31.6 million people have at least one form of eczema. In the world, 15 to 20% of children experience this, and 1 to 3% of adults. It's a lot of people. And the current solutions, the itch and scratching, the easiest to quantify, are currently only tracked through visual inspection or by using subjective scales, such as the visual analog scale shown on the right. Scales like these are extremely subjective and have been shown to be extremely prone to recall bias and response shifts. This is what is currently being used in clinical trials of new drugs. And let's be honest here, can we really trust the assessment that patients give to themselves? Remember that last time you went to the doctor and couldn't put into words which part of your body hurt? Exactly, we're not really that good at this stuff. And that is the main reason, together with others, that this method is not the best one. So let's just pinpoint. If we have subjectivity, where visual inspection and patient reports can be highly subjective, leading to inconsistencies in diagnosis and treatment efficacy. We have limited accuracy, where these methods may not accurately capture the severity or extent of eczema, potentially missing subtle or deeper skin involvement. We have overlooked triggers. Without comprehensive testing, potential allergens or irritants that trigger eczema may not be identified, leading to incomplete management. We have delayed treatment because the sole reliance on these methods can result in delays in identifying and addressing secondary infections or complications. We have patient variability, where individual differences in skin presentation and tolerance levels can complicate the assessment and management process. We have a lack of quantitative data, where these approaches do not provide objective quantitative data that can be critical for tracking disease progression and treatment response. And of course, we have the psychological bias in patients. Their descriptions of symptoms can be influenced by their psychological state, potentially skewing the clinician's understanding of the condition. So the conclusion here is that we can really do better for the medical industry, really. So as you may have guessed, there is some research in the space of using technology to track scratching, so we were presenting this. The ground truth is infrared thermal cameras used for this, primarily at night, require the person to be in front of the camera, and these need to be hand labeled, which is extremely time intensive. We also have some commercial attempts like the Itch Tracker app from Nestle Health, which can be downloaded on the Apple Watch, but it is not really that accurate. This is known as wrist actigraphy. We also have one of the most accurate devices currently out there, which is the Atom from Northwestern and a spin-out startup named Sonica Health. Atom is an accelerometer-based device which is mounted on the top of the hand as shown and can track both sleep and detect scratching. Atom has been validated in aesthetics and is able of detecting scratching behavior accurately. Then there is this multimodal sensing ring that quantifies scratch intensity using an accelerometer and a contact microphone. The device, validated through human studies, enables real-time objective measurement of scratch intensity. So, the main limitations we have for current wearable approaches is that all of the ones presented at the state of the art are for night tracking only. What about the day? We are missing a lot of valuable data here. We also have low wearability. Either things are not that comfortable to wear all day or even at night, like the ring with cables sticking out or the atom sensor, which is basically a sticker that can fall off. Or well, the infrared imaging, it is not exactly comfortable to record it all night, right? We also have some technical issues like limited power for measuring at high frequencies, and of course high costs and accessibility issues. So here comes to birth for a game-changing design for enhancing dermatological treatment. During my wrist program, I have designed a device for scratch detection that is the size of an Apple Watch. It is multimodal, wireless, portable, adaptable to different wrist sizes, flexible, and it has an insanely soft wristband. This is what we currently need for the medical industry. Part of the multimodal sensing includes a flexible PCB that integrates an accelerometer to detect tendon movements in the wrist and capture arm motions and vibrations, all related to scratching. For the wireless communication, the device has an ESP32 with an antenna, which was originally configured to establish a Wi-Fi connection. Similarly, the multi-sensing was interfaced. For the case of the accelerometer, it was with the SPI protocol. The accelerometer was set to operate at a high sampling frequency of 2000 Hz to ensure accurate and high-resolution data capture. The accelerometer data, along with the X, Y, and Z axis, is retrieved from the sensor, and the system is designed to handle the data efficiently by storing it in a buffer and subsequently transferring the buffered data into a queue once the buffer reached its full capacity. So for data sending, the buffered acceleration data is transmitted via UDP packets to a predetermined IP address on board. For all of this process, a hotspot is needed, so I used my personal hotspot, or one from my phone. So why UDP protocol? This protocol has a big advantage and a big disadvantage. It is really fast, but you cannot know if the packets arrived properly, as it has no acknowledged protocol. So to solve this issue, 3 packets are sent every time. This is the solution. The idea is to use this redundancy to ensure data integrity, considering at the same time the need for high speed. So these packets are sent from the wearable device to the computer, where the raw multi-sensing data is saved into a file for subsequent analysis and interpretation. So developing this device involved multiple iterations and hardware assembly sessions in the lab. This is the first time we had our first version where Akil and I got the Flex PCB from China, and we were doing some initial testing. After validating our first test, we decided to navigate towards the final design. This involved making it as small as possible. So my main challenge here was to optimize all the hardware from the commercial version of stuff. I did this for the rigid board design and for the Flex PCB design. In the Flex PCB was the accelerometer, which I optimized by 52% regarding the commercial version. I put that on a rigid board together with the SP32 for testing. And the accelerometer worked exactly the same as the commercial version, which was very good news. Here we can see a comparison of the graphs and some statistics related to the X, Y, and Z axis, the mean, median, standard deviation, min, and max. Basically, the values are extremely similar, which is a very good result. After that, I continued with the testing related to scratching movements to ensure that the gathered data was all right. So yeah, here is the testing accelerometer optimization. I'm doing 3 scratching movements, and here is the plotted data for the X, Y, and Z accelerations. And after the previous hardware validations, I proceeded with the final design of the device. Here's a video of the moment I finished the reflow process after the assembly. Usually the assembly is done under a microscope since the components are extremely small, so everything has to be handled very carefully. Like when you're going to the lab to assemble, you don't have coffee in the morning. That's like a must. So yeah, this is the final result of the multimodal sensor. To enclose the rigid electronics, a case was 3D printed, tailored to the board's dimensions. And there are like different perspectives. Here is the antenna. So the whole result of this was obtaining a functional device that is the size of an Apple Watch. Overall, our vision is to develop wearables that are not only useful, but also beautiful. And after finishing the final design and validating that it works, I proceeded with the data collection process. The main goal was to differentiate scratching behaviors from non-scratching behaviors. So here are two examples where on the graph on the left, the scratching behavior is performed 3 times, while on the graph on the right, I'm waving 3 times. It is evident how the scratching motions have these distinct high-frequency spikes that indicate quick, repetitive motions typical of scratching, and for the other behavior, there are more pronounced and oscillatory spikes that make sense actually with the waving act. Here are other examples. For example, here I was scratching my head multiple times. You can see the same spikes, but like multiple. Also, some running. We can see like actually similar behavior if we compare it to this one. We have some movement here, also some body language movements, and some scratching leg movements. So if we compare the graphs, we can really see a difference in these spikes and how the data is like more separate when we're talking about all the type of movements. So yeah, like this validates our device as a way of identifying scratching behaviors and differentiating them from non-scratching behaviors. I also did some tests on different types of scratching because we can do some scratching on air, on a table, on skin, on a closed skin. An interesting result after plotting this is that the graphs are not the same. If we see the scratching on air movements, this is very pronounced, and it makes sense because we don't have like any type of interference. We're doing this on air, so like the air resistance is actually enough for having more pronounced spikes. For example, if we compare the act of scratching on a table and scratching on cold skin, we can see that for the table surface, we have like more pronounced spikes in comparison to the cold skin. So yeah, these are very interesting results that need to be taken into consideration. So what are the next steps? Our next step is to make this a product. For that, we'll need to make the device fully soft, encasing it in silicone, making it beautiful, apply some machine learning to the collected data for automatic detection of scratching behaviors, then develop an app to increase usability and make this more product-like, and of course, take it to the medical industry, which is the final goal. That's all. Thank you very much.